I try to tell people a simple rule of thumb that usually keep them out of trouble. When we talk about humidifiers, if people are insistent and they have to have a humidifier, or they have a humidifier and they're going to continue to use that humidifier, is we can't have more humidity in the air than the temperature outside. So if it's 50 degrees outside and they want to maintain 50% relative humidity, by all means, maintain 50% relative humidity. If it starts to get cold outside, though, and it's 30 degrees outside, if you crank it up over 30 degrees, you're in high risk for trouble up in your attic. 30 is about the floor. You can keep it about 30 even when we get colder out. But if it's much, if you're trying to maintain 50% relative humidity in the middle of the winter, when it's 10 degrees outside, I can assure you this is what's going to happen. So over the years, we've been exposed to quite a few of these where the houses do have either a wet basement, a wet crawl space, or a humidifier. Most of these are due to humidifiers. And the homeowner had no clue on how to operate the humidifier. This is another recycled picture. Dinah had the same one. This is another good one. There's two issues here, right? Air permeable insulation up against the roof deck. When the contractor did the work in this building, which was down at the attic floor, they should have recommended pulling that stuff down. Again, when we make the attic much colder and we still have connections to the attic, this could get us into trouble just by having the insulation up there. But that really should have been taken down. But this was another humidifier. The humidifier was set at like 55%. Some easy telltales I also tell people is if you wake up in the morning, you start to see condensation in the windows, it's probably too high. Again, some more horror pictures. So let's look at it on the psychometric chart. We have 70-degree indoor air at, looks like 35% relative humidity. Right, we're in this range, so 35% relative humidity, 70 degrees. We need that air to hit a surface temperature of 41 degrees to condense. So anybody think that our roof deck in the middle of the winter is going to be 40 degrees or less? I bet they are for a significant amount of the time. And when we see these problems, they always rear their heads on the north roof first, right? Because the north roof maintains less heat all winter. So that's the first telltale things. I always tell energy auditors when we're teaching new people that are getting into this field to pay attention to the roof deck when you go to the house. A lot of these problems are pre-existing. Nobody pays attention to them. We do work in the buildings, air seal and insulate, and then they explode. They get 100 times worse than they've ever been before. Pay attention to the nails on the roof deck. Look for rust. If the nails are rusting up on the roof deck and they don't have a roof leak, there's a reason why. And people should pay attention to that before they start doing a bunch of energy work to the buildings. Tighter the house, the higher the pressures. This is an example of a 2,000 square foot house with a 3,000 CFM blower door. That's roughly an 11.2 air change per hour at 50 PA. It had a -2 depressurization in the building. That equates to a 375 CFM exhaust fan operating on the building. So as long as we're maintaining that -2 pressure, I'm sure everybody here has seen -2 pressure in the basement, in the CAS, over and over and over again, right? That's a very low pressure to see. We see pressures that are much higher than that. That's a pretty big fan operating on the building all the time, pulling fresh air in. So let's take that same house, 2,000 square foot, 8-foot ceilings, and half the blower door. Now we're down to 5.6 air changes per hour. The depressurization jumped to a -6, right? So we were at a -2 depressurization. We jumped all the way up to a -6. It's still the force of that same 375 CFM exhaust fan. Hopefully, many of you are familiar with this chart. It's a depressurization tightness limit chart. It helps us anticipate what's going to happen inside buildings. Some of you may be more familiar with the one that Energy Conservatory has in the back of their manual, which has lines going up on access. This is the same information, same chart, just a little bit more detailed. Across the top of the chart, we have blower door numbers. Across the side, we have the equivalent in the CFM of exhaust fan. And all these in the middle here are depressurizations. So for my example here, we're going to take a house that had a 2,000 blower door number. And if we had a -1.4 depressurization in the building, that's the equivalent of a 200 CFM fan exhausting on the building. If we jump the airflow up to a 400 CFM fan, our depressurization jumps to a 4.2. So that's roughly 3 times the pressure that went up in the building by doubling the fan size. And again, we can also use this chart to predict what's going to happen, right? So if we had a 2,000 CFM blower door in the house and we had a -4 depressurization, let's assume that we were going to seal up that house and half the blower door number, so we got down to 1,000 CFM. Well, that would drop our depressurization in the building to a -4.2. So I also like to look at this when contractors get into trouble in buildings, right? Because if we have pre and post blower door numbers, we have pre and post depressurization numbers, we can see, did they make the mistake before they started sealing the house, or did they cause the problem by sealing up the house? So it's definitely a chart that people should become familiar with if you're leaving natural draft equipment in the buildings. Anybody have any questions about this chart? So this is a big pet peeve of mine, to be quite honest with you. This is a single-story floor plan. We have supply ducts going to each of the rooms. 2 bedrooms here with no return. So we have a central 400 CFM return in the building. So if we close these doors in the building, this air, 69 CFM in this case, has no way of making it back to the system to be conditioned. In this case, we have 91 CFM going to this bedroom, and it has no way for it to get back to the air handler to be reconditioned. At the same time, if we close up the doors, in this case, so we closed both of these doors, we're pulling 400 CFM from a much smaller footprint. Some of the air is going to make it back to the air handler through maybe a little bit of a door undercut or some holes that may be in these walls, but the majority of that 400 CFM is going to be made up by leaks in the building. So we're going to pull in air from the outside that needs to be heated or cooled. So in home performance, I work with a lot of contractors that just swap out the equipment. So they put new furnace in, they put new water heater in, and they don't care about this anymore. They don't care that the house is operating at a -5 pressure or a -6 pressure. But they'll also be the same contractors that come back and say, on the hottest days of the year or the coldest days of the year, I did my manual J and my system isn't keeping up. Well, if you don't account for this kind of stuff, right, if we bring in 100 CFM or 200 CFM outdoor air that needs to be conditioned, and we sized right on the load, so our heating system or our cooling system is really close to where it needs to be, we're going to get into trouble. And people don't account for that stuff, right? In this case, the 69 and 91 CFM, that's 160 CFM of makeup air. A good percentage of that's going to come from the outside that needs to be conditioned. You play around with manual J's enough, put 160 CFM of ventilation system into your load and see what happens to your load. It jumps up pretty significantly. And again, this is kind of a pet peeve of mine, and we'll talk about how to fix that. This is another one that contractors a lot of times will overlook or miss. They'll walk through the house too fast and not pay attention. But there's these large kitchen hoods that can really cause big pressure imbalances in the house. I was exposed to one a couple weeks ago. It was causing a -20 pressure imbalance in the building. It was a 1,600 CFM kitchen hood that the homeowner installed himself. Very proud of his work, built a beautiful soffit, but had no idea that he would cause any of these problems, right? He's not a building science guy. He doesn't have a manometer. He's not measuring pressures. Didn't pull a permit, of course. Right? Code today says when you do this in new construction, which we deal with a lot, anything over 400 CFM, we have to install a makeup air system. And we'll show that in a couple slides forward. Be cognizant of the fans in the buildings. Sometimes you'll see some fans that are not something you would expect. Both of these fans were in the same building, and I still don't know to this day why. This was an old Comfort Partners project we went to, and it had all these different fans in the building, and I'm not really quite sure. These made the natural draft boiler and the natural draft water heater both spill. So if we didn't turn these on or we weren't paying attention to them, we would have never known that this was causing those kind of problems. So really need to pay attention to the fans in the buildings. Pay attention to returns in the CAS. They can cause significant problems. Even though this is a one-pipe, on-demand water heater, when you have a big pressure imbalance in the building like this will cause, I think this was causing a -20 pressure imbalance. This was affecting the burn here. Because this isn't two-piped, it's not using the air from the outside, and a lot of people in these programs don't pay a lot of attention to this plastic pipe stuff, right? It vents out, so we don't pay a lot of attention to it. When this turned on, this would make the CO in the system jump from like 20 parts per million up to 600 parts per million. So That may not seem like a big problem until this, the window's open, it's 10 feet away from this vent, and the air's getting blown back into the building, and it's setting off the CO alarms. That was why we got the call for this. They were setting the CO alarms off in the house, and they couldn't understand why with the equipment that they had, right? They had all this power vented, sealed up equipment, but they couldn't understand how it was getting back into the building. And none of that stuff was leaking. Again, this is a recycled picture. We just got this the other day. This is really scary. Got to use your eyes when you go into these buildings, folks. You got to pay attention to what's going on. This is really bad. Hopefully we don't see a lot of that going on. We do see tons of this going on. Luckily, in the new code book, they finally outlawed this, so hopefully we'll put a stop to this once and for all. But these pan bays down in basements, they cause lots of pressure imbalances in the basements. They're really hard to fix. I know me and a lot of other contractors have spent hours and hours in basements trying to seal all this stuff up, and it's really difficult to do it. Sometimes I'm convinced just connecting the basement to the body of the house is easier and less time consuming and serves the same function. Again, right, these are all pan based, impossible to leak, impossible to seal up really good, or really hard to seal up really well, and cause lots of problems. Filter slot covers, again, I see quite a bit of this on new and existing systems. We really need to make sure that we're covering this stuff up. This is the highest pressure zone of the air handler, right? The 1,000 CFM is produced right here. It may not be 30, 40 feet away from the system, but it's produced right there. We want to make sure that all the air goes through the filter, but two, we want to make sure that we're not causing pressure imbalances in the building, especially with natural draft equipment. We see all kinds of bad stuff that gets run through return bays over the years, electric wires, pipes. This one had a gas pipe and a condensation pipe that was run through the return bay. Looks like it's made out of cardboard, but it was actually sheet metal with insulation over top of it.